So, we're starting today's deep dive with a question that, well, it sounds really simple at first, but the more you pull at the thread, the more complicated it gets.
Oh, definitely. It always does.
Right. Because when you say type a question into one of these massive AI models, what do you think is actually happening inside the machine?
Yeah, that is essentially the question of the decade, isn't it? Because most people have this mental model that they are consulting some sort of super genius librarian.
Yeah, like you ask a question,
Yeah.
and the librarian walks back into the infinite archives.
Right. Finds the exact book, reads the page, walks back to the front desk, and just recites the answer to you perfectly.
Right, that completely feels like the transaction we're having. I ask, it knows, it tells me.
But that isn't really what's happening at all.
Not even close, right.
No, it's much more like asking a very confident, very charming improvisational actor.
Okay, an actor.
Yeah, an actor who maybe read the entire library 2 years ago, but is currently locked in an empty room with absolutely no internet access.
Wow, okay. That paints a picture.
Right. They remember a lot of facts, sure. But if you ask them about something highly specific that happened yesterday, or something incredibly niche that was in a footnote of a book they barely glanced at.
They aren't going to just say, I don't know, are they?
Never. They are going to improvise.
Which means they hallucinate.
Exactly. They hallucinate. They make things up that sound totally plausible because, fundamentally, their job is just to complete the pattern of language.
Not to be factually accurate.
Right. Accuracy isn't the primary directive, and that is the absolute bottleneck of artificial intelligence right now. We have these incredible reasoning engines, but they are trapped in the past.
Because they're cut off from whatever their training data cutoff date was.
Yes, and because of that, they are highly prone to confident lying.
Which brings us perfectly to the source material we are diving into today. It's tackling this exact problem head on.
And it's a fascinating approach.
The paper is called, and bear with me, the title is a bit of a mouthful. It's RQ-URI-AG, Learning to Refine Query for Retrieval Augmented Generation.
It does sound incredibly technical. RQ-RAG. It kind of sounds like a droid from Star Wars or something.
It really does. But the concept behind it is genuinely a turning point for how we build these systems.
Yeah.
And the mission for our deep dives today isn't to get bogged down in all those acronyms.
No, definitely not.
We want to dissect the actual methodology of this new approach. We're going to look at how these researchers are teaching an AI not just to answer questions, but to actively realize when it doesn't know the answer.
Which is huge.
And then, once it realizes that, to actively go out and research it.
And not just research it blindly either. We are talking about teaching an AI how to rewrite your bad questions, break down complex logic problems into steps, and basically act like a genuine investigator.
Instead of just a static encyclopedia.
Exactly.
So to really appreciate the solution they've come up with, we have to nail down the problem first. We already mentioned hallucination. But the industry solution for a while now has been something called standard RAG, right?
Yeah.
Retrieval Augmented Generation. Can we set the stage for the listeners? What exactly is standard RAG and why isn't it enough?
Sure. So standard RAG is basically, it's like duct-taking a search engine to the large language model.
Crude, but effective.
I mean, in theory, yes. In a standard RAG setup, you type a question. The system takes your exact words, verbatim, and just pastes them into a search bar.
Okay.
It grabs whatever the top 5 documents are that come back, feeds those documents directly into the AI, and essentially says, here, use this text to answer the user.
It sounds logical enough on the surface, like if I ask, what is the capital of France? It searches, what is the capital of France?
Right.
It finds Paris in a document, and it tells me.
Yeah, and for simple trivia like that, it works totally fine. But the paper we are analyzing today makes a strong argument that standard RAG is actually broken at a fundamental level.
Because language is messy.
Because human language is incredibly messy, and search engines are very literal. The authors identify 3 specific failure modes where standard RAG just falls flat on its face.
Let's walk through these 3 problems, because I think anyone listening who has used an AI search tool has probably experienced these, even if they didn't know the technical term for what was going wrong.
Oh, for sure. So the first failure mode the methodology addresses is ambiguity.
Ambiguity?
Yeah. The paper uses this really fantastic example from the world of sports. Imagine a user just types the phrase, goals in a season, into the prompt.
Okay, goals in a season. That's pretty vague.
It's extremely vague. What do they even mean? Are they talking about football? Hockey, Basketball.
Right, and are they talking about a single player or an entire team?
Exactly. The paper points out that, for instance, in the English Premier League, the record for the most goals scored by a team in a season is 106. That was Manchester City.
Okay.
But the record for a single player is 34.
So if you just take that exact string, goals in a season, and dump it into a search engine.
You get a complete mess of results. You get a soup of numbers.
Mhm.
You get documents mentioning 106, documents mentioning 34. You might get 50 from some completely different league.
And a standard art model is just looking for patterns in whatever you hand it, right?
Right.
It's trying to be helpful.
Right. So it might grab that 106 number because it shows up near the word goals and confidently tell you the most goals scored by a player in a season is 106.
Which is physically impossible. That would be a superhuman feat for one player.
It would. But the model doesn't inherently know that. It just sees a high probability association in the retrieved documents.
Yeah.
That is the fundamental danger of ambiguity. The search engine gave the model bad data because the initial query was bad.
And then the model confidently reported that bad data back to the user.
Exactly. So the methodology needs to create a model that realizes, hey, this prompt is vague. I need to figure out if they mean a player or a team before I just start grabbing numbers.
Which brings us to the second problem they outline.
Right. The second problem is complexity. And this is where we get into what researchers call multi-hop questions.
I love these. These are the logic puzzle ones.
Yeah, the paper gives a classic example of a multi-hop query. Who is the mayor of the city where the author of The Great Gatsby was born?
Oh man, my brain hurts just hearing that all at once.
Right. It's a lot to process.
But I could solve it if I stop and think about it in pieces.
You can, because you have a human brain, and you know how to plan a sequence of actions. You break it down intuitively. Step 1. Who wrote The Great Gatsby?
F. Scott Fitzgerald.
Step 2. Where was he born?
St. Paul, Minnesota.
And step 3. Who is the current mayor of St. Paul?
I have absolutely no idea, but I could easily Google that specific question.
Exactly. You could Google that specific piece of the puzzle. But think about what a standard RAG system does with that original prompt.
It takes the whole thing.
It takes that entire long, convoluted sentence, who is the mayor of the city where the author of The Great Gatsby was born, and it pastes that entire string into the search bar.
And the search engine probably just goes, I have no idea what you're asking for.
You get absolute garbage back. You might get random literary analysis articles about Gatsby, or a list of mayors of New York City, or a biography of Fitzgerald that doesn't mention mayors at all.
But you almost certainly do not get a single page that perfectly connects all three of those distinct dots for you.
No, because standard RGAD tries to do it all in one giant bite. It completely lacks that step-by-step procedural process. It literally chokes on the complexity.
Okay, so standard ARGA fails on vague questions. It fails on complex logic puzzles. What is the third problem?
The third problem is irrelevance. This is essentially the noise problem. Because sometimes searching is actually the exact wrong thing to do.
Like if I just open the chat and say hello.
Right? Or how are you doing today? Or can you write me a poem about the rain? If you have a standard RAG system that is hard-coded to always search first, which many of them are,
Yeah.
it will dutifully take that and search the internet for, write me a poem about the rain.
But what does it even bring back? Weather reports.
Weather reports, amateur poetry blogs, lyrics to pop songs about rain, and suddenly the AI has all of this totally random text stuffed into its context window that has nothing to do with the actual task of just writing you a nice poem.
It just creates noise.
It massively distracts the model. It is like trying to write a heartfelt, creative poem while someone stands next to you shouting historical precipitation statistics.
That sounds awful.
It is. The paper mentions that previous research clearly shows in relevant context can significantly degrade the quality of an AI's answer. It confuses them.
So looking at these three massive flaws, the core goal of this new RQRID methodology, this refined query approach, is to build a model that actually has the judgment to know when to search, and more importantly, how to search.
Yes. It needs to stop being a passive recipient of whatever the search engine spits out and actually take the wheel.
Let's unpack that take the wheel idea,
Yeah.
because that leads into the high-level approach the authors use. They are proposing a fundamental shift in the architecture of how the model generates text.
They really are. They are moving the paradigm from pure text generation to what they call action generation.
Action generation. What does that actually look like in the methodology?
Well, normally a language model just predicts the next word, word, until the sentence is done. But in this new architecture, the authors are training the model to generate a special token first.
A token, like a piece of code or a command.
Think of it like a function call. Or even simpler, think of it like the AI raising its hand in class. When the model receives a prompt, before it ever tries to formulate an answer, it hits a decision gate. It internally asks itself, do I currently have enough information to accurately answer this?
And if it decides it does, like if I asked it what 2 plus 2 is,
Then it just answers, no search needed. But if it says no, if it realizes it needs external help to be accurate, it generates that special token.
and that token is the trigger. It triggers a sort of research mode.
Exactly. It enters refinement mode, it intentionally pauses its answer generation, and it uses one of three very specific tools or capabilities that the researchers explicitly taught it to use.
Let's walk through those 3 tools because the paper is very specific about how these map onto the problems we just discussed. What's the first tool?
The first tool is rewriting. This directly handles the ambiguity problem we talked about earlier.
A goals in a season problem.
Right. If the user's query is goals in a season, the model, in refinement mode, might rewrite that query to something like most goals scored by a single player in an English Premier League season.
So it basically translates the user's vague, messy thought into clean, search engine-friendly language.
Yes. It optimizes the query for the search engine to ensure it gets exactly the right document back.
Okay, that makes sense. What is the second tool?
Decomposition. This is the heavy lifter for those complex logic puzzles. It takes that convoluted Mayor of Gatsby's birthplace question and actively breaks it down into a chain of smaller queries.
It builds the stepping stones.
It generates the first sub-question. Where was F. Scott Fitzgerald born? It sends that to the search engine. It reads the result and gets the answer, St. Paul.
And then it stops.
No, and this is the really magic part of the methodology. It then uses that newly acquired information to generate the next sub-question. Who is the mayor of St. Paul?
That is genuinely impressive. It is doing iterative research, it's learning new facts and using them to dig deeper.
It acts exactly like a human researcher would. And the third tool it has is disambiguation.
How is that different from rewriting?
It's somewhat similar, but it's specifically focused on clarifying user intent when a specific term has multiple valid meanings. It ensures the search results align with what the user most likely actually meant, rather than a secondary definition.
Okay, so we have rewriting, decomposition, and disambiguation. These are the superpowers that RQRAG gives the model. But here is the million-dollar question for this deep dive. How do you actually teach a computer to do this?
Right, because you can't just program it with standard rules.
And you can't just go to the internet and download a massive ready-made data set of the inner monologues of expert human researchers. That doesn't exist.
No, standard datasets are just pairs, question and answer. They don't show the work. They don't show the bad search queries or the refinement process or the dead ends. They just show the final result.
So the researchers had a massive data problem, which brings us to step 1 of their methodology, dataset construction.
Yes, and honestly, this is the part of the paper that fascinated me the most. Because since they didn't have a teacher, they had to build their own.
They automated a massive data creation factory to train their model. Walk us through this pipeline. How do they take a raw, simple question and turn it into a step-by-step lesson for the AI?
It is a brilliant 4-phase process. Phase 1 is simply classification. They took a massive pool of tasks, just raw questions from existing open-source datasets, and they fed them to a much larger, highly capable model. Specifically, they used ChatGPT, GPT 3.5, to act as the teacher.
So they asked ChatGPT to look at the questions first.
Right. They asked the teacher model, look at this question. Is this part of a multi-turn dialogue? Does this specific question require decomposition? Or does it need disambiguation?
They're basically sorting the mail before they open it.
Exactly. They need to categorize what type of problem it is so they know which of those 3 strategies to apply. Once they have it classified, they move to phase 2, refined query generation.
This is where they ask the teacher model to actually write the search terms.
Yes, and they use very strictly formatted prompt templates for this. They explicitly tell ChatGPT, hey, do not answer this question. Instead, based on the category we just assigned, give me the exact search query or queries that would best help you find the answer.
Ah, so they are forcing ChatGPT to show its work. They're saying, what would you type into Google to solve this?
Exactly. If it categorized the task as needing decomposition, the prompt forces ChatGPT to break the question down and output the subqueries. So at the end of phase 2, they now have a massive collection of perfect search queries generated by a very smart model.
But a search query is useless without the actual search results.
Which perfectly leads to phase 3, the search itself. They take those refined queries generated by the teacher, and they actually feed them into a real live search engine.
They don't simulate it.
No, they go to the live internet. In the methodology of this paper, they treated the search engine as a complete black box, and they primarily used DuckDuckGo.
Okay, so they run the search on DuckDuckGo and collect what comes back.
They scrape the top results, usually the titles and the short snippets of text that appear on the search results page.
Okay, let me make sure I'm following the methodology so far.
Yeah.
So now they have the original raw question, they have the refined query that ChatGPT wrote, and they have the real search results from DuckDuckGo. Is that the final training data?
Not yet. And this is where we hit phase 4, contextual answer generation. And I need to stress this. This is arguably the single most crucial step in the entire methodology.
Why is phase 4 so crucial?
Because you have to remember, the original source datasets they used, they already had the correct answers attached to them.
Right. If the question was pulled from a trivia dataset, the answer key is sitting right there in the file.
But the researchers deliberately throw that original answer away.
Wait, really? If the dataset literally has the verified correct answer, why would they throw it out?
Because of the hallucination problem we talk about at the very beginning. Imagine this scenario. ChatGPT generates a brilliant search query, but DuckDuckGo fails. The search results come back empty or totally irrelevant.
Okay, so the model has the question, a failed search, and then nothing useful.
Right. Now, if you take that failed search sequence and you append the perfect correct answer from the original dataset at the end of it, what are you teaching the AI?
Oh, I see. You are teaching it a very dangerous lesson.
Yeah.
You are teaching it, ignore the search results. Even if the evidence you found is garbage, just output the answer anyway from your internal memory.
Exactly. You are explicitly training it to hallucinate. You are teaching the model that the entire search step is just theater and that it should just rely on what it already knows.
Which completely defeats the entire purpose of building a RAG system in the first place. You want the model to be firmly grounded in the retrieved document.
Precisely. So to prevent this, the authors went back to the teacher model, back to ChatGPT, and said, look, here is the refined query we generated, and here are the specific search results we got back from DuckDuckGo. Now, we want you to write a brand new answer based only on the context provided in these search results.
That is incredibly smart. So the training data becomes perfectly aligned logically. It says, here's what I asked, here's how I refined the search, here's the exact evidence I found, and here's the conclusion I drew based strictly on that evidence.
It creates a perfect causal chain. And they took it a step further with a strict filtering process. If ChatGPT looked at those search results and couldn't formulate a valid answer, if the search was a total bust, they discarded that entire data point.
They deleted.
Deleted it. It didn't make it into the training set.
So they're essentially curating a success curriculum for the student model. They only want to show it examples where the entire research process went smoothly from start to finish.
They filter out all the noise and failure. This ensures that the student model learns that strict rule. The final answer must always come directly from the retrieved evidence.
And that rigorous process leads to the final data structure they use. In the paper, they refer to this mathematically as equation 1, but if we explain it verbally, it basically acts like a script for a play.
It is exactly like a script. To the computer, the final training example looks like a chronological sequence. You have the original input, followed by the special token, followed by the refined query, followed by the retrieved documents, followed finally by the contextual answer.
It's a behavioral script. When you see X, do Y, then read Z, then say A.
And that beautifully transitions us into step 2 of the methodology, generator training, because now that they have this massive curriculum of perfect scripts, they need to actually teach the student.
And the student in this paper is a smaller model, right? I think they use Llama 2.
Yes, specifically the Llama 2 7B model, so a 7 billion parameter model.
For our listeners who might not track parameter counts, how big is that in the grand scheme of things?
In the current world of large language models, 7B is considered quite small and very efficient. It's the kind of model a hobbyist could potentially run on a high-end consumer graphics card or a really good laptop. It is magnitudes smaller than something like GPT-4.
And their goal is to teach this relatively small, lightweight model to act with the combined intelligence of the massive ChatGPT teacher and a live search engine.
Yes, and the way they train it is through something called end-to-end auto-regressive training.
Okay, that sounds like a very dense technical term. Let's break that down without using any math. What does autoregressive actually mean in this context?
Autoregressive simply means the core function of the model is just predicting the next word in a sequence based on the words that came before it. It's how basically all modern language models function. They read the text so far and calculate the probability of what the next word should be.
But the end-to-end part is the key here.
Right. End-to-end means they are training the Llama 2 model on that entire multi-step script we just described all at once.
So during training, they feed the llama model the raw question. And it has to learn that the correct next word to predict isn't the start of the answer.
Exactly. It learns that when it sees a complex or vague question, the highest probability next step is to output that special token.
It essentially learns impulse control.
That is a great way to phrase it. It learns impulse control, and it learns how to plan. It learns that the correct behavior is to trigger a search. Then it learns how to formulate the refined query. Then the training system artificially inserts the retrieved documents into the sequence.
And then the model learns to read those inserted documents and finally predict the words of the final answer.
Yes. So it isn't just memorizing facts about the world during this training phase. It is fundamentally learning a procedure. It is learning the methodology of how to conduct research.
It's procedural learning, which is profound because it shows that even a very small model can perform incredibly complex tasks if you just teach it the right sequence of steps, rather than trying to force it to memorize the entire internet.
It punches way above its weight class because it has a methodology.
This all sounds amazing in theory, but I imagine there has to be a catch when you actually deploy this. When the model is running live, what the paper calls inference time, it has to make choices on the fly.
It does.
What happens if it looks at a prompt and it genuinely isn't sure whether it should use the rewriting tool or the decomposition tool?
That exact dilemma is what step 3 of the methodology addresses. They call it sampling strategies. Because you are right, at the moment of decision, the model might be uncertain. So the authors implemented what is known as a tree decoding strategy.
A tree, like a decision tree.
Visually, yes, imagine a tree branching out. The model receives a user question. It hits that first decision gate. It thinks, well, I could rewrite this to be more specific, but it also thinks I could decompose this into sub-questions.
So instead of just guessing one and hoping for the best, it splits.
It splits. It simultaneously explores multiple trajectories or paths. Path A might be a rewriting strategy. Path B might be a decomposition strategy. Maybe Path C is a slightly different rewriting strategy.
And because each of those paths uses a completely different search query, they're going to get completely different search results back from the engine.
Correct. Different queries inevitably lead to different documents, which ultimately lead the model to generate different final answers at the end of each branch.
Okay, so now the system has, say, 3 or 4 completely different final answers to the same user question. How on earth does it know which one to actually show the user? It seems like this methodology just created a brand new problem. You went from having one dubious answer to having 5 possible answers.
It is a very classic AI dilemma. Exploration versus exploitation. You explored all these multiple paths to gather data, but now you need a reliable mechanism to select the single best one. The authors propose 3 distinct selection methods to judge which branch of the tree is the winner.
Let's go through these 3 selection methods, because they are quite different. Method A is called perplexity-based selection.
Yes, often abbreviated as PPL. Perplexity, in the realm of language models, is essentially a mathematical measure of surprise.
Surprise.
Yeah, how surprised the model is by a sequence of text based on its training. A low perplexity score means the text flows very naturally and logically according to the patterns the model knows. It's entirely expected.
So how does the system use that to pick a winner?
It looks at the entirety of a path, the refined query, plus all the retrieved documents, plus the final generated answer, and it calculates the total perplexity for that whole sequence.
It asks itself which one of these complete stories makes the most logical sense from start to finish.
Mathematically, yes. It picks the path with the lowest overall perplexity. It's basically the system saying, this particular path feels the most coherent and smooth.
But there's an obvious flaw there, right? A smooth liar is still a liar.
Exactly. That is the critical weakness of perplexity. Just because a sequence of text flows beautifully and sounds highly logical doesn't necessarily mean it is factually true, especially if the search results were subtly wrong.
Which leads us to their second way of choosing. Method B, confidence-based selection. How is confidence fundamentally different from perplexity?
Confidence-based selection is much more focused. Unlike perplexity, which judges the entire journey, confidence looks strictly at the final destination. It only evaluates the final answer generation step.
It ignores all the messy work that led up to it.
It completely ignores how hard the search query was to formulate, and it ignores how noisy the retrieved documents were. It simply looks at the final response and calculates how mathematically certain the model is about those specific tokens.
So it's the difference between I'm 99% sure the answer is blue versus I am 60% sure the answer is red. The system just picks blue.
Exactly. It goes with the answer it feels most strongly about, regardless of the path.
But again, bringing it back to hallucinations, models are incredibly famous for being confidently wrong.
They are. High confidence doesn't guarantee factual accuracy, which is why the authors introduced the third, and generally the most effective, method, ensemble-based selection.
Ensemble, that sounds like a voting system.
It is exactly a voting system. It relies on the wisdom of the crowd, or in this case, the wisdom of the branches.
How does the voting work?
The system runs all those multiple paths we talked about. Say, one path uses rewriting, another uses decomposition, another uses disambiguation. They take entirely different routes through the search engine.
Right.
But let's say 3 of those wildly different paths all independently arrive at the exact same final answer. Say they all conclude the answer is April 20th.
Oh, I see. Then April 20th is highly likely to be the true answer.
Yes. The system groups identical answers together and simply adds up their individual confidence scores. The logic is incredibly sound. If multiple different research strategies using different search terms and reading different documents all point to the exact same conclusion, that agreement implies truth.
That makes total sense. If you hand a complex problem to 3 different human experts and they use 3 different methods to solve it, but they all come back with the exact same number, you're going to trust that number.
Exactly. And the paper actually proves this out. They found that this ensemble strategy consistently performs the best, particularly for those really complex multi-hop tasks where a single path might easily get derailed.
Yeah, one really fascinating detail in the methodology section was this analysis they did on the upper bound.
The upper bound analysis is so revealing.
Can you explain what the researchers meant by checking the upper bound?
Sure. They essentially ran a diagnostic on the whole tree decoding process. They asked a hypothetical question. Okay, we generated this massive tree of possible paths. What if we had a perfectly omniscient selection method? Was the objectively correct answer actually present somewhere in that tree, even if our perplexity or confidence metrics failed to pick it as the winner?
So they wanted to know if the right answer was at least available on the menu, even if the AI ordered the wrong thing.
Exactly. They wanted to evaluate the pure retrieval capability of the methodology separate from the selection metrics, and the results were staggering. They found that the potential accuracy, the upper bound, was incredibly high. On some complex data sets, it was over 80%.
Wow, over 80%. So that completely validates the core methodology. The refined queries are working. The model is successfully finding the right information out there on the internet.
Yes, the research phase is highly successful. The methodology proves that a small model can find the truth. The remaining bottleneck for future research is simply improving the selection metrics so it picks the winner from the tree every single time.
That is incredibly promising. Let's zoom out a bit from the mechanics. Why does this specific methodology matter so much in the broader landscape of AI? How does it fundamentally compare to what everyone else is doing?
I think the most important comparison the paper makes is contrasting their approach, which they call search on demand, with the industry standard of indiscriminate search.
We touched on this briefly with the hello example. Indiscriminate search is just searching for absolutely everything, no matter what.
Right. Standard RAG is a hammer, and it treats every single user prompt as a nail. It searches blindly. RQRAG, through this methodology, learns to be a scalpel. It acts on demand. It has the agency to choose not to search if the query is a simple greeting or basic math.
But it also has the agency to search multiple times in a row if the query is a complex logic puzzle.
Exactly. It scales its effort to the complexity of the task.
And what about another major industry trend? Chain of thought reasoning. We hear that buzzword constantly, the whole let's think step-by-step prompt.
Yeah.
How does RQRAG compare to that?
Chain of thought is a fantastic technique. It forces the model to slow down and map out its reasoning. But there is a massive limitation. Chain of thought relies entirely on the model's internal logic and internal memory.
It's a closed system.
Right. It's like asking a really smart person to sit in an empty, locked room and think really, really hard about a fact they don't know.
If they don't know the capital of some obscure region, thinking harder about it isn't going to magically make the fact appear in their brain.
Exactly. In fact, if they think too hard, they might just hallucinate a highly logical sounding but completely fake answer. RQRG solves this because it relies on external verification.
It opens the door to the room.
It's like asking that smart person to stop thinking, walk out of the room, and go to the library. The external grounding is everything. The authors actually show in the paper that their tiny Llama 7B model, when equipped with RQRH, frequently outperformed massive models like standard ChatGPT that were only using internal chain of thought reasoning.
Because a decent student who is allowed to use an encyclopedia is always going to beat a genius who is locked in an empty room.
Genuinely, yes. That is the undeniable power of external grounding in these systems.
Now, we always had to be critical on the deep dive. We can't just hype up the success stories. If we look closely at this methodology, what are the foundational assumptions here? Where are the weak points? What could potentially cause this whole system to collapse?
That is the right question to ask. The methodology relies on three massive dependencies. First, and most obviously, there is the assumption of the black box search.
Meaning the search engine itself.
Yes. The entire methodology assumes that DuckDuckGo or whatever search engine you plug into it is inherently reliable.
But if the search engine goes down,
Or, more likely, if the internet is suddenly flooded with highly optimized SEO spam or active misinformation about a topic,
then the model fails. Garbage in, garbage out.
exactly. The RQRIG model is completely agnostic to the truth. It is only as good as the documents the search engine decides to hand it. It has no mechanism to verify the actual credibility of the source website. It only verifies relevance to the query.
That is a significant vulnerability. What is the second assumption?
The second assumption is teacher quality. Remember how we spent all that time on step 1, dataset construction? The entire curriculum was generated by ChatGPT. The methodology inherently assumes that ChatGPT was a perfect teacher. It assumes it generated optimal refined queries and accurately synthesized the contextual answers.
But if the teacher model hallucinated during the training data generation,
Then the Llama 2 student model literally memorizes those hallucinations as the correct procedure. The student can only ever be as good as the teacher's curriculum.
and the third assumption.
The third assumption is contextual availability. The whole pipeline hinges on the fact that the actual factual answer mathematically exists within the top few search results retrieved.
The paper specifically used the top three, right? That is a remarkably tight window.
It's incredibly tight. If the correct answer is buried on result number 5 or on page 2 of Google, the Llama model simply never sees it. It is invisible to the system. So the quality of that refined query generated by the special token has to be absolutely laser precise to guarantee the correct document lands in those top 3 slots.
That is a lot of pressure on the query generator.
It is.
So to synthesize all of this, because we have covered a massive amount of technical ground regarding this methodology, if a listener wants to mentally model how this works, what are the 3 core pillars of the RQRAG approach?
Let's summarize it cleanly. Pillar 1 is data.
Meaning the automated pipeline.
Right. Automating the creation of perfect query refinement answer examples, using a larger teacher model to simulate the ideal research process, and strictly ensuring that the final training answer is always derived purely from the retrieved search results to actively prevent the model from learning to hallucinate.
Got it. And pillar 2,
Pillar 2 is training.
taking that curriculum and feeding it to the student.
Exactly. Taking a smaller, highly efficient model and teaching it a behavioral script. Teaching it to actually output actions, those crucial special tokens that trigger rewriting, decomposing, or disambiguating before it ever attempts to generate a final answer.
It learns procedure, not just facts. And the final pillar, pillar 3.
Pillar 3 is inference, the live environment.
That's the tree decoding and the voting.
Yes. Using tree decoding to simultaneously explore multiple distinct research paths, trying different queries and subqueries, and then utilizing robust selection metrics like confidence and ensemble voting to identify the most accurate and reliable path through the noise.
Looking at those 3 pillars, it really represents a massive philosophical shift in AI development. We are moving from a paradigm of static answering, just regurgitating memorized training data, to dynamic investigating.
It really feels like the AI is fundamentally growing up. It's learning to use tools just like humans do.
That is the absolute perfect way to put it, because this methodology suggests that the true future of artificial intelligence isn't necessarily just about making the central brain bigger and bigger. It isn't just about endlessly scaling up parameters to memorize more data.
No, it's about developing better research skills.
It is about agency. It's not about the AI knowing absolutely everything. It's about the AI knowing precisely how to find out.
Exactly. It is about the cognitive ability to look at a complex problem, formally recognize the boundaries of what you don't know, and then methodically use external tools to fill in those specific gaps. That is what genuine intelligence really looks like.
And honestly, that is exactly what makes diving into a paper like this so exciting. It isn't just theoretical, it provides a concrete, step-by-step roadmap for how we actually build that kind of intelligence.
It really does. It shows the path forward.
And that is a fascinating thought to leave you with today. The next time you are faced with a complex problem in your own life, and you sit down and ask yourself, okay, how do I break this down? What do I actually need to search for first? Just remember, somewhere out there in a lab, a 7 billion parameter model is being trained to do the exact same thing.
And if we follow this methodology, it might just beat you to the right answer.
Thanks for joining us on this deep dive. We'll catch you next time.